So we'll wait for a minute and then we'll start.
Yeah, okay.
Okay. I think we can start now.
Yeah, sure, Kritika.
Okay.
Hi, Praveen.
Okay.
This is
Hi.
Shubham.
Hello, Sumar.
So good afternoon, everyone. Thank you for joining today. Welcome to the seminar series by ITP in Climate Studies, IIT Bombay. Today we have with us Dr. Praveen Kumar Pothapakula. Dr. Praveen is a researcher at Karlsruhe Institute of Technology in Germany. He did his PhD in geosciences from Goethe University, Frankfurt, Germany. He has an MTech degree in climate science and technology from IIT Bhubaneswar. For his PhD work, he has worked on exploring information exchange in climate system and climate models. He was awarded IIT Bhubaneswar Institute Medal for Best Academic Performance. He would be moving to ETH Zurich, Switzerland, to develop ICON model for MetaSwiss from March 2023. Today, he will be delivering a seminar on his PhD topic, that is exploring information exchange in climate system and climate models. So, welcome, Dr. Praveen. Over to you.
Thank you very much for the nice introduction. And thank you for inviting me. Uh, I wish I would have been there in the campus, but yeah, unfortunately, I have to give an online seminar. But maybe in the future, we will see. I would like to talk about my work, which majorly I did in my PhD, entitled Exploring Information Exchange in Climate System and Climate Models. I worked with Professor Boda Arons at Goethe University of Frankfurt, and currently I'm working with Professor Joachim Pinto at Karlsruhe Institute of Technology on Markov chains. So I would basically try to introduce the concept a little bit and try to explain the methodology, then try to explain three important topics which were involved in my PhD, and then I would do some conclusions, and then I'll try to see my try to project my future directions. Uh, yeah, before that, I took this photo this morning at my house. So it's kind of snowing slightly here in Karlsruhe, which is pretty common. But luckily, this month it has been quite a decent amount of snow, which was matching climatology. Um, so yeah, I just wanted to show this figure just for some motivation, let's say. Um, Moving forward to my talk, so the introduction goes like this. So we know that the Earth system is a complex nonlinear system, which consists of different components, namely the land, the ocean, the atmosphere, the ice, and so on. And we know that these components interact non-linearly with each other. And one way actually to look at these interactions is by thinking that these interactions are contemplated or can be thought of as information exchange between different subcomponents. What do I mean by information exchange? Let us consider a simple complex system which consists of various nodes, let's say y1a, x, and y2 and b. And these nodes are emitting binary signals with respect to the time. Here you can see n minus 1 and n plus 1 represents time, and these nodes are actually emitting different signals. Now, if we observe carefully at n plus 1, which is, let's say, the future time step, x has emitted a binary symbol 0. Now, the question to ask is how does x decide to emit 0 and why not 1? So when you go into the dynamics of the system, you know that the information received by X is actually from nodes Y2 and Y1, which are given in red arrows. So X receives information from Y2 and Y1 and then decides on emitting a symbol 0. This is how I understand information exchange. Now, the objective of the thesis is basically try to see how various components in the climate system are actually interacting with each other and try to quantify them in terms of information exchange. For example, we know that subcomponents in climate system interact through exchange of mass, momentum, and energy. And what we have is actually a time series for different parameters in the climate system. For example, wind speed, snow, rainfall, and so on. So we have a time series now. So what we can do with the information exchange is try to go back in time and see how these parameters or variables are interacting with each other, and then try to quantify the information exchange to actually understand the climate system. So I come to three important research questions in my thesis. One is, first of all, the basic question to ask is whether the information theory methods actually can detect reliable information exchange. And for that, I have used idealized and real world applications, and I'll show you some of the results to convince that the information exchange methods actually work. Then the question number two is basically try to use these information exchange methods to actually quantify the information exchange from the global climate models into the regional climate models in the process of dynamical downscaling. And the last question is, we at Goethe University, we developed a coupled model, which means we have coupled Mediterranean Ocean to the European domain, atmospheric domain. And then we want to really quantify the information exchange from the Mediterranean Sea into the atmosphere and want to see if the coupled system or the coupling actually adds value to the climate simulation. So coming to the methodology, the basic, the first standard concept of information theory was proposed by Shannon in about 1948 in this paper, where he describes entropy of a random variable x is equal to the summation of p of x into log p of x, where p of x represents the probability outcome of a single event of the given random variable x. The units of entropy are basically given in nats or in bits usually. And the formula goes like this. So to understand it in a very simple terms, when h of x is equal to 0, that means you don't have any uncertainty of the given random variable x. If h of x is non-zero, that means there exists an uncertainty in the given probability distribution of the random variable x. Now, the next concept is mutual information when you have two variables x and y. So the mutual information quantifies the information shared between x and y. The problem with mutual information is that it's symmetric quantity. That means if you have mutual information value, the uncertainty that you reduce is actually symmetric. But this is not something that we actually always want. So for that, Schreiber has introduced a terminology or a concept called transfer entropy. which is equal to the deviation of the transitional probabilities of xn plus 1 condition on the past of xn, and also xn plus 1 condition on the past of xn, and also another variable y. I don't want to go into the details of the formula, but what I would like you to know is that when transfer entropy from y to x is non-zero, that means information is exchanged from y to x, but not y to vice versa. So when transfer entropy from y to x is 0, that means there is no information exchange from variable y to variable x. This is popularly used in some of the causality studies that we see in the recent literature. Now, the last concept that I would like to put forth here is the method introduced by Liang from the fundamental concepts of derived from the information theory. So what they propose is we have two-dimensional deterministic system x1 and x2, which are governed by the dynamics f1 and f2 as a function of x1 comma x2 comma t. So what they actually propose is when there is an information exchange from 2 to 1, the value of this quantity is actually non-zero. So when it is 0, then there is no information exchange from 2 to 1. If it is non-zero, then there is an information exchange from 2 to 1. So this method from hereafter is referred as information flow linear. Now, these are some of the methods that I developed or tested in my PhD thesis. So I divide the information theory methods into linear and nonlinear. In nonlinear, so we further I divided the estimators like this. For example, binning, kernel, and Cascow. So this is how actually you construct a PDF, and that's how the name goes. So when there's a binning approach, you basically divide the probability distribution into n number of bins, and then you can use kernel smoothing, or you can use number of nearest neighbor estimators through by building the PDF. And I don't want to spend much detail on the methodology here. So now to understand the concept or to prove that the information theory methods work, what I try to consider is a simple two-dimensional system, x and y, where yn plus 1 is equal to 0.5 times yn plus some noise, and xn plus 1 is equal to 0.6 times xn plus c times yn plus some Gaussian noise. Here we can see that y is actually exchanging information to x through the coupling coefficient c, but not vice versa, because you don't have any coupling between to x and y. So when c over here is 0, so you don't have any information exchange from y to x. But then when you try to increase the value of c from with an increment of 0.1 till 1, you should see that the y is actually exchanging information to x. So when I apply the methods, so we should see that y should exchange information to x, but not vice versa. And here are the results of these methods. So on the y-axis, you see information exchange in NATS for information flow, transfer entropy, and nonlinear transfer entropy methods. And on x-axis, you see a coupling coefficient. So when the coupling coefficient is 0, you see that both information exchange from x to y and y to x is 0. And then when you increase the coupling coefficient, you see that the information is actually exchanged from y to x, but not vice versa. And this is exactly what we have seen in our governing equations. Now, we also try to see the sensitivity of these methods on different time series length, because in climate, we always are handicapped by the limited amount of time series. So when we kind of reduce the time series from 5,000 to 1,000 and 500, 200, we see that these methods are actually sensitive to the time series length as well. And on the top, we have linear estimators, and on the bottom, you see a non-linear estimators. So binning is actually not working very well. And when we see kernel and Cascow, you see that the transfer entropy values are actually giving realistic.
Somehow, Praveen, you got muted.
Yeah, thank you. I hope the
Now,
mute was
now
not.
we can.
Yeah,
Yeah.
not for the long time, I hope.
No, just for a few seconds.
Okay, thank you, Professor Salman. Yeah. Um, so the nonlinear estimators over here, you see that we both kernel and Casco are actually giving good results, except binning. But I must admit that we had to play a lot with this free tuning parameters. That means the kernel width and the number of nearest neighbor estimators to get this result. It was not always easy. So somehow you have to play with these free tuning parameters to get the result. So that was one of the difficult part that we also mentioned in our paper. Now coming to a nonlinear system, so we took a very simple Hanon map, which are both coupled to each other by CYX and CX to Y. So we have an information exchange from both directions, which are governed by the coupling coefficients Y to X and X to Y. To go into the results, let's first I would come to the nonlinear estimator over here. So through binning or kernel, so you see that as information coefficient of as C of xy, which is the coefficient coupling coefficient from x to y, is actually increasing in the y direction. You have an information flow from x to y also increasing in the y direction over here, but not in the x direction, and this is vice versa here. So this is something the dynamics of the system is well replicated by these nonlinear methods, but over here you see T linear and information flow linear, they actually fail to replicate the dynamics of these nonlinear systems. But this is expected, of course, because one might argue these are linear estimators. But somehow, some of the papers in climate studies, they have used these linear estimators for nonlinear parameters, and then they publish some interesting results, which of course are under question, because you see that the linear estimators are actually failing. So one should be using the nonlinear estimators, but I can understand that these are a bit difficult to apply. Now coming to the real world applications, what we did is try to apply information flow from the Pacific Ocean over here, this is an Inyo region, to the Indian SST, sea surface temperature. So over here, what you see is the information exchange from the Pacific to the Indian Ocean at a time lag of 3 months. So we found significant information exchange from the Pacific to Indian Ocean, and we claim that this is something like an Indian Ocean dipole pattern over here. So we noted that there is an information exchange from Pacific to Indian Ocean, and perhaps this is a sign that IOD is actually perhaps influenced by the Pacific. Now, the other way, we also applied information exchange from the IOD index to the whole Pacific Ocean. And we also see some signals with linear and also nonlinear estimators to the Pacific at a time lag of 6 months. So what we found, or what we concluded, is that we see a bidirectional information exchange between Indian and Pacific Ocean. And this is well established in the literature somehow. And this is also proven by this information exchange methodology. But we also try to do similar thing for European surface temperatures and NAO index, and we also found bidirectional influence, but then that was really unrealistic bidirectional influence. So we found that sometimes these parameters are always influenced by a common variable which are driving both variables at a time. So one might say that IOD and Pacific are actually interacting with each other, but one can also hypothesize that there is a common driver which is actually influencing the both. So this is a red flag that before we draw conclusions with these information exchange methods, one should be really careful in interpreting the results. So the conclusion for question 1 is that yes, these methods are useful, of course, but of course these nonlinear estimators have to be tested and tuned for robust results, and these are sensitive to the time series length. And one important thing is we should always be careful with interpreting the results when there is always a common driver which is influencing both. Coming to the second question, so far we have chosen only two variables, that is information exchange from x to y and y to x. But we want to see what happens with information when you have two sources and one target. That means two variables which are influencing the target variable. For that, the two sources for me to to take consider IOD and ENSO together and see how these are influencing the Indian summer monsoon rainfall. So the first goal is basically to apply the information exchange methodology to observations or reanalysis data, then try to apply to the GCMs, and then try to apply to the RCMs. So what we can quantify is how much of information we observed, which is exchanged from these two oceans to the Indian monsoon in real world in climate system, and then try to understand if this information exchange is well replicated in the GCMs, and then when you downscale the GCMs, is that information realistically replicated in the RCM? So we go by a chain to actually see what really happens in terms of two source and target information exchange. So what we did is with collaboration from ETH Zurich, Switzerland. So what we did is to take Cosmo model, which is a regional model over here or in Germany. It's well used in Germany. So we took a Cosmo CLM model and downscaled three global climate models, namely MPI ESM, NOR ESM, and EC Earth for about 150 years, and then try to evaluate our simulations in terms of information exchange. I would encourage you guys to look into this paper, and if you want to use this data, I'm happy to provide the data. And of course, these data are also available on ESGF data notes. Now, to understand two source information exchanged to a target, so Y and Z are two sources here, and X is the target. So we can divide the information exchange into four parts over here. One is unique information shared by Y to X, unique information shared from Z to X, and then there is a redundant information that really that is of no use for us. Then we have a synergy between Y and Z to X. That means uh, you can only say something about X when you know Y and Z together, but not alone. So this is very interesting property over here, namely this synergy. So when you have a synergy, so it means that you should know the states of Y and Z together, but not alone to actually predict X. Moving forward, what I show here is the information exchange plots from IOD and ENSO to the precipitation over the Indian subcontinent in various observational data sets, GPCC, Aphrodite, and the reanalysis ENSO. So on the left, you see information exchange from IOD to precipitation. You see significant values over here. And then from ENSO to precipitation, you also see significant values over Indian subcontinent. And then when you look both IOD and ENSO together to precipitation, almost whole of the India is covered. The most interesting figure over here is the right side one. So you see synergy. So this means that the red color over here, the positive values, show synergy between IOD and ENSO in predicting precipitation. That means when you know IOD and ENSO state together, the Indian monsoon core region, we have a synergistic effect. That means when you want to reduce the uncertainty of precipitation in this region, you want to know IOD and ENSO state together, but not alone. So this is an interesting feature that we found with this information exchange methodology. And that is actually also replicated in Aphrodite dataset and not really well in NCEP analysis because of the coarse resolution. Now the question to ask is the synergy pattern replicated in the RCM, which when we downscale the RCM with three GCMs, MPI ESM, NOR ESM, and ECF. So we see that only one.
Praveen,
yeah.
in between there is a question, maybe
Yeah.
for, I can see Professor Raghu has a question. So
Yeah, okay.
Yeah, I mean, I understand the methodology, but the way it's being applied, I'm not sure at what stage the physics would come in, because the big challenge about understanding IOD and so impact on monsoon has been that monsoon peaks in June, July, August, IOD in SON and ENSO in DJF, and we don't even know if IOD and ENSO are really independent. All indications are that they are not. So this is going to be just kind of a technical application of a methodology, or are you at some point able to extract physics out of it?
Yeah. Yeah, of course. Yeah, it's a good question. So ultimately what I realized when applying this methodology is, yes, we apply a methodology and we get to see some results, but ultimately we have to fall back to physics to actually understand why this happens. So I would perhaps in the later stage of the presentation, I will try to show some of the figures where we have a moisture transport from ENSO and IOD. They both are actually compensating with each other when we have a ENSO, when we have an El
No,
Nino.
but I
And,
mean, before you go there,
yeah.
sorry, the lead lag is not considered here, right? You are just taking data and looking for information exchange. It's not clear the lead lag relations between them.
Yes. Yeah. Yeah. First of all, I checked lead lag relations for almost all the period. But what we are now here looking is the summertime, the June, July, August, and the state of IOD and ENSO at that particular season, at that particular time. I also checked it with different lead lags, but the signal is actually diminished when you have different lead lags. Yeah.
Okay, so that's kind of the physics I was talking about. If IOD
Yes, yes.
peaks in SON and the signal is weaker, then I have to. Okay, thank you.
Yeah. It's always important that we check the peaks of IOD and ENSO, influencing them. But what I tried them, so but as I said, so we have a diminishing signal. Um, yeah, but here what we see is the signal at the particular state of IOD and ENSO in the summer, in the June, July, August months. So moving forward.
Praveen, there is another question. If we just quickly take, if there is a doubt or something, I think.
Yeah. Okay.
Yeah, I can see Tejashvi as a question.
Yes. Yes. So can you hear me, Dr. Praveen?
Yes. Yeah.
Hi, my name is Tejasvi. I'm a PhD student here. I have two questions. One is, what does negative values of synergy mean? Positive,
Yeah.
I can imagine that there is a signal which only comes when there are two values together, two variables together. But how do we interpret negative values?
Yeah, it's a good question. Thanks for asking. So with the information exchange methodology, what one could actually calculate is a term called net synergy, not synergy itself. So net synergy is something like is equal to synergy minus redundancy. So this is the best that we can calculate from the information theory methodology. So the positive values indicate synergy is actually greater than redundancy. And when there is a negative value, that means it's a redundant information. So the blue color over here, which are negative values, these indicate it is a redundant information.
Okay. Okay.
So I would perhaps explain I have it in the additional slides. I have a formula for it. So maybe on the layman terms, this is how I can interpret.
Oh, yeah, I
Yeah.
understood. Thank you. Thank you. Another question is,
Yes.
did you use only June, July, August, September time series for it, or full length years time series?
I tried both, but I'm currently showing you only the June, July, August values.
So do you stack them together like June, July, August of first year, then next immediately after June, July, August of second?
Yes, that's how I did it. Yeah.
So then I wanted to ask, wouldn't it create problems at any point when unique information or something is calculated at lags? Because then it will try to put 1st June of next year with 31st September of previous year.
Yeah, when you are considering lags, it's always a problem. This is directly calculating the same month. So you have a same month for same month precipitation.
I see. So there are no lags involved.
You can try the lags, and somehow you have to play with it to escape that particular problem that you say during the lags.
Okay. Yeah.
Yeah,
I mean, Praveen, so continuing that, I mean, just to have a discussion on this, because this is an important point. What Tejasvi has asked and what Raghu has also asked. So Raghu was saying that, in September, IOD reaches the peak. So it's very important to understand how the things are actually evolving. And that way we have to take the lead lag relationship. And that's very important even for the prediction also. Even if you don't have the lead lag relationship, it may not add to the prediction. Now, considering that, and if you are using just 4 months, then you cannot really consider lead lag, because you're stitching the data set and your lag information is getting wrong. That's correct. And at the same time, if you consider the entire year, then your monsoon signal will get diluted.
Yeah.
So my question here is that, what Raghu was also trying to ask is that, then is such method really applicable for such cases? Or, what do you think? Because we also have been trying to think about it and we never got a proper solution how to really take care of such seasonal data set, because without lead lag it may not finally add value. So that's the point probably that Tejasvi was also trying to ask.
Yeah, yes, it's an unsolved problem for me too. So perhaps we can discuss a in detail what are the solutions that can be done over here. But this is a problem that is always there. How to solve this issue?
Okay, thank you. Thanks.
Yeah, yeah, yeah. But the other point that one can also think is in not in terms of prediction, but for example, whether these kind of patterns are actually replicated in the models itself, because you can also think this problem in terms of evaluating the models, because what we see over here is the synergy, of course, at the same time, but the 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 aim is that the climate models also have the same patterns like this one when you try to apply this methodology. So in that case, if this is another picture where this methodology is actually used to actually evaluate a climate model, let's say. And this is also quite important because we always want to have a similar kind of signal inside the model, inside the RCM and the GCM. So it's also very important that these kind of methods are used for climate model evaluation. So the goal of the work is basically try to look this in the perspective of model evaluation. So perhaps this is quite useful in that terms. So what we see here is that the Cosmo model, which when driven by NOR-ESM, so we see that some amount of net synergy is actually replicated over the domain, and whereas in MPI and ECR, so we don't see such kind of a signal over there. And we saw why this happens, and we found that the IOD and ENSO signal is not pretty realistic in the ECR and MPI ESM GCM. And whereas in NOR-ESM, we found that the signals are a bit realistic, and that's why we see such kind of a signal over here. And this is also very interesting result because we always think that the RCMs actually reduce biases, but somehow they inherit biases from the GCMs, and they are unable to replicate these kind of patterns. So this is something also interesting that we found in one of our paper. Yeah, so the conclusion is that one should actually be careful in selecting a particular GCM for our for the target that we are actually looking at, because the RCMs are actually sometimes taking the biases into them and then not producing a realistic signal. So this is something that we wanted to conclude in this paper. And finally, what we did is in our group is to couple ocean into the atmosphere, into the regional domain, and we coupled Mediterranean Ocean to the atmosphere, which is a Cosmo model, and the ocean model is NEMO-MED. So we have a typical cyclones over Europe. This is an European domain. So there's a typical cyclone called Vb-cyclones, which actually are traveling from the Mediterranean Sea over here into the continental Europe, carrying a lot of precipitation. Sorry, carrying a lot of precipitation into the Europe. So what we wanted to see is whether the Mediterranean Sea is exchanging information during these 5B events in our regional coupled model, setup. So for that, what we did is to run an evaluation simulation with ERA 20C for about 1951 to 2005, and also try to use a historical simulation with EC Earth, and then also have a future with RCP 8.5. And we wanted to see if there is a significant amount of information exchange from the Mediterranean Sea into the Vb-cyclone events. So this is one of the result. So on the top, you see the evaluation run, which is run by ERA ERA 20C with the Cosmos CLM model. And you see over here in the Mediterranean region, so you see a significant amount of significant amount of information which is exchanged from the Mediterranean Sea for the three catchments. These three catchments are catchments over Europe, and we try to calculate the precipitation over there and try to see the information exchange values. However, in the historical simulation, we don't see such a signal over here. And this is interesting because we use the same RCM over here, but just the driving data is different. So ERA 20C data, we see an amplification in the signal in the Mediterranean, but however, with historical simulation, we don't see such a signal. So again, the biases in the GCMs when downscaled with the RCM. The RCM is actually taking the biases, and then what is interesting here is that the process itself is actually changing. So this is not a good signal for regional climate modeling community, but this is what we have found. So so this in for the question 3, the information exchange methodology also helped us to get some insights into the climate modeling, let's say. And finally, I would skip this slide. So I have talked about these results earlier. Yeah, and a little bit about the future. So we have an icon model, which is icosahedral triangular grid. What is the goal of the Exclaim project, which is done by ETH, is to take the icon model and try to run it on GPUs and try to scale up and speed it up and see how much of speed has increased to conduct kilometer scale global climate simulations. So I would go there as a postdoc from March and try to see how I can improve it. So I also did some of the work on icon already. So it is published in this paper. So what we did is to conduct simulations over this Tibetan plateau with about a 3 kilometer resolution with icon model, and we also have a lot of models which were used, for example WAF, the Cosmo, and MPAS, and so on, to actually conduct a kilometer scale ensemble to look if these ensembles are actually providing added value into the precipitation and some of the events that they have selected. So they have selected 3 cases, a monsoon convective system, the whole monsoon period for August, and then one snow event. I don't want to go into the details, but what we see here is that the icon model is actually predicting very well, or not predicting. I have replicated the precipitation over here very well when compared to the observations over here, and it matches the exact location. But however, for the other simulations such as WAF and so on, we don't see that kind of a signal at the particular location. But however, this is very soon to say that icon is pretty much better, but this might be just a chance also. I will skip this slide, and thank you for your suggestions. Yeah, I mean, I look forward for your suggestions. Thanks for listening. Yeah.
Thank you, Praveen. Questions from
That last part, kilometer scale, that's regional model, or is it global?
Yeah, it's the domain is yeah, this one. So it's a regional model. Yeah.
I think kilometer scale is meaningful only when we talk about global scale, right? Regional scale models have been done at all kinds of high resolution. Case scale modeling is useful and meaningful terminology when we mean it's done at global scale.
Yeah. but still the domain over here is quite expensive to run a 3 kilometer simulation too.
Yeah, but that's not determined by computational expense. It is determined by the physics that what they want to resolve. A nice paper by Julius Lingo and Tim Palmer and so on. Why we need case scale beyond Stevens. That has good physics questions. That I mean, regional models are run for urban scale. I don't know. Suvimal has run it, but some people have run it at 1 kilometer scale. I think for urban flooding and so on. So regional models is not a big deal.
Yeah, but the goal is to conduct a climate scale simulation for about 10 years or so, and to look into the added value of the CPS over the cortex Cortex scale, for example, like 0.44, 50
I'm
kilometers.
not questioning the goals. I'm just saying the K scale is a very nice, meaningful terminology for global models.
Okay. Yeah.
Azhar, you have asked a question in the chat box. If you want, you can switch on your video and ask Dr. Praveen directly. Azhar, are you there? Okay, maybe I'll read out Azhar's question, and then Vikram has also raised his hand. So Azhar's question is, why was the 12th realization considered when EC Earth model is selected?
Yeah.
And it's a very long
Always.
question.
Yeah. Yeah, but I'm not really sure of this. But generally, we use R12 ensemble. But I'm not really sure what's the change in the physics, or what kind of a realization is that. But generally, for all the regional downscaling simulations, so R12 was used from the EC Earth at least, unlike the other ensembles. Maybe if someone here has a better answer, maybe I would also like to learn this.
Okay, Azhar, does that answer your question, or okay, meanwhile, I'll ask Vikram to please switch on his video and ask his question. Vikram Singh Chandel. He's our PhD student. Vikram, are you there? Okay, I don't know. Maybe some signal issue. Maheshwaran, can you go ahead with your question? I can see your hands raised.
Yeah. Thank you very much. Thank you very much, Dr. Praveen. This is Maheshwaran from IT Hyderabad. So I have a question here. Like when you talk about the statistical significance of this transfer entropy that you have calculated, so how did you calculate whether these are like statistically significant? Did you use any color noise or like at the background, and then try and then look for the sporadic values that these values get on generally?
Yeah, thank you for the question. So I tried to use surrogate samples, try to shuffle the time series and try to take about 100 samples and try to calculate the standard deviation and then calculate the significance out of this sample estimation of transfer entropy.
Thank you. Thank you very much.
Yeah, thanks for the question. Yeah.
Vikram is here, sits next to my office. So Vikram came here. So Vikram will ask question from here.
Hello.
Okay, sir.
Hello, can you hear me?
Yeah, hi Vikram. Yes, I can hear
Hello.
you.
Actually, I have one question regarding to that synergy and uniqueness of information that you use.
Yeah.
How different is this from Professor Praveen Kumar's approach? You must have read those papers, right?
Yeah. Yes, Professor, I also met Professor Praveen Kumar. So the way that these unique and redundant and synergy they have computed is actually different from different model different groups actually. So for now there has been no, how should I say, there have been no consensus on how do we calculate the unique and the shared information or the synergy and so on. Some people say you neglect the redundant information if it is too less and then just calculate synergy. So for me, I have not tried to go into the part where it is disputed. So that's why I only calculated synergy minus redundancy, which you can calculate directly from the standard approaches of information theory, which is synergy minus redundancy. Yeah. So I did not go into the calculation of exactly synergy or redundancy, where Professor Praveen Kumar and his group has actually tried to compute synergy and redundancy by taking some strong, let's say, assumptions. Yeah. But here I only showed robust results which directly come from information theory methodology. Yeah. But still, the way that they compute these quantities, unique and synergy, is still there's no agreement on this. So yeah, you can try different methodologies if you are interested. Yeah. It's
Okay,
a nice
thank you.
question.
I have another question actually.
Yes, sure.
So this is related to the application in Indian Ocean Dipole and summer monsoon. So actually this is related to the initial discussion that we were having. So how did you take the lags while calculating the influence of IOD and so?
Yeah, I think I have answered this question partly. So I tried different lags, but now what I showed is that you have a June, July, August signal directly. So can say it's a zero lag over here on a monthly scale.
Okay.
Yeah.
As Tejosi asked, so there must be some error due to the stacking. So I know this is an unsolved problem right now. So, but there should be a method or a metric so that we can quantify how wrong might our results be actually.
Yeah, this is also true. Yeah, it would be
Yes,
nice to have a paper like which says, okay, we have tried this approach and this much of deviation is what we get, and perhaps this deviation is much larger than signal and this is insignificant result. I mean, this is also really a nice paper. Yeah.
Okay, that's all from my side. Thank you.
Thank you very much for a nice question.
Actually, Vikram's question is also, sorry, somebody else there, Shiva?
You can continue. Actually, discussion can continue, and then later on someone can ask.
Yeah, that's my last question. So this question of validation, when you earlier on you said linear methods were used and you use nonlinear method, but
Yeah.
computationally is nonlinear method much more expensive for this information theory?
Yes, sir. Sure. It's
So I think
expensive.
even there, Vikram's question about validation is if you use judiciously choose linear methods and they give you the results that can be validated,
Yes.
then obviously that's the economic way to do it. Okay.
And also a robust way to do it. But it's always nice to have a nonlinear estimator, for sure. But then again, it's a bit difficult, computational, expensive, and also there are few free tuning parameters on how do you calculate the PDF and so on. So that's also a challenge. But then the point is that we go in the direction to solve such kind of a problem to get nonlinear estimators.
So I think Tejasvi have one more question. Tejasvi, you may ask.
Yes. So Dr. Praveen, you told about that kernel methods are better than binning. I have two questions. One is this unique synergy minus uniqueness synergy minus redundancy when you computed. Did you use kernel fitting or it was binning?
No, I did not use binning. I tried to use k-nearest neighbor estimators and kernel estimators, and
Okay.
also the linear estimator. So I only tried to take some intuition out of the results only when these three methods gave me the same signal, or let's say I only consider it robust when the three methods are actually giving the same signal or so.
I see. So k-nearest neighbor, kernel, and the third
And
one,
the linear estimator, let's say.
I see. So that's interesting. My main question is, in all this exercise, you told that it's a challenging task to tune the kernel. Can you guide us with a thumb rule or something that can help us tune a kernel? What could be how should we proceed for tuning the kernel? Means anything precipitable there.
It's a very difficult question that you're asking me. No, I can't give a thumb rule for these kind of things. But one thing that I always do is to look into the number of kernels and try to see if the data is fitting well, if there are enough number of blocks that go inside each kernel and so on to make it as smooth as possible. But if you ask me a thumb rule, it's really difficult to give. And this is a problem that I also face. So you're not alone, or at least I'm not alone. So we are all on this together. So it's always a challenge. Yeah.
Yeah. Thank you.
Yeah.
Okay, so Maheshwaran, you have your hand raised still. So do you have any question further?
I have one more question, Dr. Praveen. This is regarding the estimators I've used. Like you've used kernel estimators, and then you've used the other binning, and then the histogram methods. Like of these, like which do you like recommend?
I don't recommend a single estimator. What I recommend is try to look into kernel, Karskov, and perhaps linear when you are in a linear regime or a weak nonlinear regime, and see if these three methods agree. And if these three methods are agreeing, and then you fine tune it, and then, for example, I just go to the example over here. Yeah, so you see that I tested different estimators, and they are actually agreeing between among themselves. So this is when I get confidence that okay, this signal is realistic. Yeah, I mean, I have also done statistical significant tests, but at the same time, what I proposed in this paper is that you should have consistency in these methods, and if the methods that you have are consistent, then you can claim that the signal is robust. So I perhaps cannot give you a single estimator, but I have a feeling, personal feeling, that the k nearest neighbor estimator is quite good sometimes compared to other estimators in terms of nonlinear. So k nearest neighbor is something that I can depend upon, not all the times, but yeah.
Thank you. And then last one, like, did you deal with any problem associated with zeros in your time series when you're working with these estimators? Because
Yes, yes, yes.
how did you deal with that?
Yes, again, there's no solution. But what I try to do, because it's on a monthly scale, so you can skip that problem. So, but always zeros and in precipitation time series is a challenge on how to deal with it. But I'm not able to give you any answer for that. Yeah, thumb rule. Yeah, and you also know why. So it's
Yeah,
very
yeah,
difficult.
true.
Yeah, yeah, yeah.
Thank you so much, Praveen. Thank you.
Thank you. Yeah.
That's what
So anyone else have question?
Okay, maybe I just stop sharing the screen. Yeah.
Okay.
I don't think there is any more question, right, Ritika?
Yes, sir. So should we close the session?
Yes, yes. Thanks, Praveen, for your nice talk and nice interactions.
Yeah, thank you, Professor Vimal.
So before closing the session, I would request Ajanya to take a group picture, requesting all the attendees to please switch on their video for a moment. Are we done?
I think Ajanya is muted.
Yeah, I have.
Okay. Okay. So thank you so much, Dr. Praveen, and thank you, everyone.
Thank you, Kritika, and also thank you, Shiba. It was very well organized. Thank you very much.
Thank you.
Have a nice evening. Yeah.
Thanks.
Thank you, Dr.
Thank
Praveen.
you.
Bye.
Bye.